Hello, my name is Carolin Stellmacher and I'm a PhD student in Germany at the University of Bremen. I will share our work today on simulating changes of object weight during the interaction in VR. Our paper carries the title Experiencing Dynamic Weight Changes in Virtual Reality through Pseudo-Haptics and Vibrotactile Feedback. And this is joint work with all of my co-authors listed here, Feri, Tanja, Jan-Niklas and Johannes. Conveying a sense of object heaviness in VR has been a challenge. The majority of previous research focused mainly on conveying absolute weights using haptic devices, pseudo-haptics, or a combination of both. However, there is limited research on simulating a change in object weight, for example, when filling a virtual glass of water. This lack of responsiveness of the haptic feedback during the interaction limits a comprehensive experience of objects in VR. The previously explored techniques rely mainly on complex hardware that change the actual weight of the interaction device. For now, the question remains if we can utilize previously explored pseudo-haptic approaches also for simulating changes in object weight. And this would lighten the hardware complexity and enable the usage of standard VR systems. The known method for simulating virtual weight is increasing or decreasing the control display ratio, short CD ratio, between the control hand, here the physical hand, and the display hand, which is the virtual hand in VR. The result is a displacement between both hands, and you probably encountered this effect before when adjusting the mouse cursor speed on your laptop. For simulating absolute weights in VR, this manipulation of the CD ratio is done before the interaction. It then either amplifies or compresses the arm movement when lifting the object. In our novel approach for simulating changes in weight, we go beyond this and manipulate the CD ratio during the interaction. For example, the increasing weight of a mug that is being filled with water then triggers a slight negative displacement on the y-axis. Our expectation is that users will then subconsciously compensate the displacement through an upwards movement of their arm to secure the lift of the virtual hand and the virtual mug. A higher arm posture then means more strain on the muscles and might induce a pseudo-haptic illusion of a growing weight. The mechanism looks similar for a decreasing weight. Here, the CD ratio is initially adjusted according to the heavy weight of the filled mug. As the water now leaves the mug, the positive displacement on the y-axis is triggered. And the expected adjustment of the arm posture here would result in a physical downward movement of the arm to again compensate and stabilize the mug at its original position in VR. The lower lift means less strain on the muscles and might induce an illusion of a decreasing weight. In our implementation, the extent of manipulation is directly influenced by the water level in the cup. We applied a maximum CD ratio of 0.6, similar to previous research, as this was often the threshold for the displacement to become noticeable by users. To strengthen this perceptual illusion of weight change, we additionally applied growing and shrinking vibrotactile feedback. The amplitude of the vibration then provides a second weight cue and mimics the water's impact on the inside walls of the mug. For example, the water stream hitting the empty mug is simulated with an initial high amplitude, which then lessens with a growing water volume and its decreasing impact on the mug. When the water leaves a full mug, an initial strong vibration mimics the strong water flow, which lessens with the shrinking amount of water. To test the techniques, we conducted a study in VR with 18 participants in which they performed two types of interactions, filling a mug and pouring out a mug. So in the one scenario, the weight dynamically increases, and in the other, the weight dynamically decreases while users hold onto the mug. Each participant experienced the weight change simulation in 3 conditions. First, the base condition where no simulation is applied. Second, the CD condition where only the change in the CD ratio is applied. And third, the CD haptic condition where we change the CD ratio plus add additional vibration. We tested the illusion with 3 weight changes visualized by 3 different water levels. And our study was guided by the question if both techniques can induce an illusion of weight change and if that enhances the user's feelings of immersion. Participants were the MetaQuest system and were placed inside the virtual environment built with Unity. The study task was simple. Fill or pour out 3 mugs, one by one. A virtual platform in the middle offered either a water tap or a container to catch the virtual water. After each interaction, mugs were placed on the right side on the table. To understand the weight perception, we applied a mixed method approach taking quantitative and qualitative measurements. After each interaction, participants rated their perception of how much the weight changed on a 7-item Likert scale in VR. And after each condition, participants filled out a questionnaire to rate the quality of their weight experience of that particular condition. And items covered aspects such as arm effort or efficiency. Participants also rated their immersion and their task load. Participants were also asked to think aloud during the experiment, and we observed participants' view in VR and provided a free text input field at the end of the study for more subjective feedback. The results showed significant differences in the Likert scale ratings between the different water levels in regards to the perceived extent of weight change. For example, filling a mug up to the maximum received significantly higher ratings than filling it just 2/3 or 1/3 in the weight techniques. This similar but slightly weaker staircase effect is also visible in the ratings of the other 2 conditions. And we can make similar observations in the pour interaction. So from this we can learn that participants did perceive an increase or decrease in the mug's weight during both interactions, and they were also able to differentiate weight changes to different extents. This finding is also highlighted in the custom weight questionnaire. For example, ratings for question 7 show that participants felt the mugs having different weights during the task when they were exposed to a weight simulation technique. And ratings for question 8 show that participants felt the weight of the mug change as the water volume changed. Looking at the same data just with a different grouping highlights the significant differences across the conditions. For example, here in the case of filling the mug up to the maximum, we see that both weight simulations had a significant positive impact on the experience of the weight change. This same observation can be made consistently across all water levels, and again also for the pour interaction. We can learn from this that both simulations allowed participants to experience the weight change. However, we can also see that the vibration did not significantly enhance the weight change effect further as we hoped it would. But the current data indicates a potential for a positive trend, which could be further investigated in future work. The effectiveness of both weight change simulations is further emphasized through the ratings of the custom questionnaire that participants filled out after each condition. Question 1 assessed if participants thought that the mugs had initially the same weight before the interaction. This was denied in the poor interaction in both weight conditions. And this is in line with our expectations, as the mugs here initially had different weights. Question 2 assessed the same aspect, but asked if all mugs had the same weight after the interaction, and this was again denied in the fill interaction here in both weight conditions. And this is again in line with our expectations, as all mugs had different weights after being filled with water. In regards to our initial expectation that users would adjust their arm posture to compensate for the virtual hand displacement, we can see that participants did indeed feel in both weight simulations an increased effort to keep their hands steady. This indicates that the displacement had the desired pseudo-haptic effect that we were aiming for. At the same time, ownership of the virtual hand received similar high ratings. Finally, however, we did not see a significant difference in participants' immersion in VR. In conclusion, our work shows that the known pseudo-haptic technique of manipulating the control display ratio is also effective for conveying a sense of changing object weight during the interaction. However, in our study, we could not see an improvement with the additionally applied vibration, nor an improvement in immersion. In the future, research could focus on exploring different implementations of the vibrotactile feedback to enhance the pseudo-haptic effect of weight change. As our work only explored filling or pouring a mug, future studies could test other types of interactions that do not have the rotational hand movement, for example, packing a bag. And this was the research work for our paper, Experiencing Dynamic Weight Changes in Virtual Reality through Pseudo-Haptics and Vibrotactile Feedback.